names and formulas for ionic compounds. I hope this was just a refresher and a review. Make sure that when you are writing formulas for compounds that they will be neutral overall. I do not want to see symbols for charges in a final formula for a compound. If you need to write it as you're coming up with the formula, that's fine. Make sure they're not there. Okay, help me out. What are the formulas going to be for these substances? Calcium oxide is CaO. Barium phosphide, Ba3P2. Phosphide with an IDE is just phosphorus. Okay, copper 2 carbonate, or excuse me, copper 1 carbonate. U2, CO3. And here's our first opportunity to talk about the lab. My group that had reaction 4 used copper 2 carbonate. Was it this group? Okay, y'all tried to make that way too complicated. Okay, not a combustion reaction. It was a decomposition reaction. Okay, so it decomposed into copper oxide, which was what color? Black, and then carbon dioxide. Okay, they started with just copper 2 carbonate, heated it up, decomposed. Okay, tell me the formula for ammonium nitrate. NH4NO3. Which group had that reaction? The NH4NO3 in water. Somebody did. Okay, this group did. What happened when the ammonium nitrate dissolved in water? What did you observe? Yeah, it got cold. It got cold. When ammonium nitrate dissolves, there is a temperature change. Okay, your solution should have felt cold. That was the sign it was a chemical change. The calcium chloride group, which calcium chloride is CaCl2, should have felt the temperature increasing when it dissolves. Okay. All right, last one of these is aluminum sulfate, which should be Al2SO4 3. Make sure that sulfate is in parentheses. We don't want 43 oxygen. Okay. Naming ionic compounds. Hopefully the first one you got really easily. NaCl is sodium chloride, good. Li2O is lithium oxide. And then we've got iron 2 chloride, iron 3 chloride. Again, this is where we can use the charge of our anion to figure out the charge of those metals that have multiple charges. Last one, magnesium nitrate. Okay. We all good on that? Okay, great. I hope that you did well with the balancing. I want to just pause and take a look at the particle diagrams. I anticipate you did really well with the balancing of these because they are pretty simple. One thing to think about as we're working on particle diagrams is to consider the physical state. Okay, so whether or not you did that this time around, that's all right. But start to think about that. If you know it's a gas, how are you going to show that? If you know it's a solid, how are you going to show that? If you know it's a liquid. Okay, all of those things. And then also, I did hear a couple of groups talk about needing to draw a key or make a key for your particles. Okay, if you have done that with your particle diagrams, go ahead and do that. These are my representations. Things to consider with particle diagrams, besides what we just talked about, use a reasonable number of particles. You need to show enough particles to show what's going on, but you also don't want to draw particles forever, right? For me, I'd like to see no less than 3 particles as the lowest number. That gives you enough to be able to show what the physical state is. If you have less than 3, it's hard to tell whether it's supposed to be a solid, liquid, or gas. Yeah. Yeah, the iron oxide in that case, like I can pretty easily do that. If I wanted to draw more particles, I could, but I also didn't want to fill up my whole box. Yeah, great question. Yeah. Great question. So in a case like this, where you're just showing the reaction, I would want you to use a ratio based on the balanced equation. Does that make sense? So in the first case here with the formation of ammonia, I used 3 as my least number and then scaled up from there by using 6 hydrogens and then making 3 ammonias. And then in my second reaction, I just used 1 of each, right? Or like followed the coefficients. When we get into talking about stoichiometry next week, we may not have exact ratios. We likely won't. And so we would want to show any excess in our final picture as well. Great question. One more thing before we move on. Right now, I don't care a whole lot about how you're drawing your molecules or formula units so long as your particles are connected. I don't care how they're connected. This is just how I drew them. If we want to get really technical, I should have drawn my ammonias in a different way because they don't have a trigonal planar geometry like I drew. They are actually trigonal pyramidal. Does that matter right now? No. Will that matter on the AP test? No. Okay. But you should consider things like what I have here. Let me really focus in on this. We'll get better at this, but what do we know about ionic compounds? Well, they have positively charged ions and negatively charged ions. What do you know about positive ions and negative ions? They attract one another, right? But then if we have positive and positive ions, they will repel. So when you draw ionic compounds, consider that, right? Try to alternate your charges. Now, they're not going to form the way I drew them here. I just put them in a line like that because it was easy, but that's not really what's going to happen. And that's okay, right? I think they look like little caterpillars the way that I drew them, but I did alternate positive, negative, positive, negative. Make sense? Okay. I hope that the last 3 were easier than you thought they were going to be, especially that middle one. How'd we do? Remember when you're balancing equations to give me the most simplified form that you can for your coefficients while still using whole numbers. Questions at this point? All right, let's look at the mole ones. Okay. Remember, because atoms are so small, we cannot count them. That's why we use the mole. Okay, we know a mole is going to be equal to Avogadro's number, which is 6.022 times 10 to the 23rd particles. But since we can't count them, that's why we use molar mass. Right? I do not care when you're doing a problem if you show me how you calculated the molar mass. That's why I just wrote the molar mass. Okay? Know that if you got the molar mass wrong on an assessment on something like this, I'm not going to count the whole thing wrong. I'm going to use the molar mass you gave me. Okay, same thing will happen on the AP exam. They call it no error carried forward. I will grade the same way. I know many of you probably learned to do conversions using dimensional analysis. That's great. Use that. Okay. I prefer using proportions, so that's what I'm going to use most likely when I'm doing answer keys. Please know I don't care how you solve a problem. I will never ask you to solve a problem in one specific way. What I ask you to do is to show me your work, make it clear enough for me to follow your process, and I ask that the method you use makes it is possible to get the right answer. That's all I care about, right? Everybody's brains work differently. You shouldn't be put into a box to do the work the way I say it must be done. So I don't care. Do it your way. Cool? All right, I'm going to show one of these as dimensional analysis. I'll show one of them as, I'll show the other 2 as proportions. We'll just check answers as we go. We'll also talk about sig figs. Somebody asked me about that. Yeah? Okay. So 50 grams of calcium bromide, we want to go into moles. If we're going dimensional analysis, we're going to go 50 grams of CaBr2. We're going to go opposite to cancel. So I'm going to put grams here. I'll put moles here. 1 mole is my molar mass, 199.88. I'm going to cancel. right? And then I'm going to solve. Okay, I'm going to take 50 divided by 199.88, which I think is 0.250 for my final answer. Am I remembering right? Okay. We want three significant figures. 0.250, this is moles. Okay. Can you tell me what a sig fig is? Yeah, that's what I thought. Do you know how to find sig figs? Do you know how to round to sig figs? Okay, so, but you probably, if you do know what a sig fig is, you probably memorized like a definition for a sig fig. So let's talk about what a significant figure actually is. When you're making a measurement and you're collecting data, the piece of equipment that you use determines how many significant figures there are in a measurement. The significant figures that are reported tell us every digit of the measurement we know for sure, plus one estimated digit. Does that make sense? Okay. That's what a sig fig is. So what we know from this number here, 50 grams as 50.0 grams, is that the balance used to measure that was able to tell for sure, with 100% certainty, the tens place of the value, the ones place of the value. But then the tenth place, that first decimal, was estimated. Those are our sig figs. Yeah? So when you're taking a measurement on a piece of digital equipment, the device itself estimates the last digit. That's why you'll see like fluctuation on a digital balance while it's figuring out what that last digit's going to be, making the estimate. If you're using a piece of equipment like a graduated cylinder, you have to look at the markings to figure out how many sig figs you're going to record. So I'm holding two graduated cylinders. One is a 25 milliliter graduated cylinder that has a mark for every milliliter. That means I can read down to the milliliter for certain, and I'm going to estimate one more place. So I would estimate to the 10th place using this graduated cylinder. My 10 milliliter graduated cylinder has a mark for every 10th of a milliliter, which means I can estimate past that, right? I'm going to estimate to the 100th place. Yeah? Does that make sense? Does that help you understand why sig figs are so important? Because we have all these rules for how to figure out sig figs from numbers to tell you about the piece of equipment. We have all these rules for doing math with sig figs to tell you that when you do the calculation, your number can't be any more precise than the least precise piece of equipment. That's what it means. That's where they come from. Okay. All right, give me a second to reconnect here. It kicked me off. And then we'll do math for the next one. I'm going to use a proportion for this. Like, I don't care what you use. All right. I like proportions. We use proportions almost exclusively in Chemistry 1 now, and it just makes things easier, I think. So if I'm going to solve using a proportion, mathematically you're going to do the same stuff, but here's what it would look like. If I'm going moles of oxygen in, 3.0 times 10 to the 24th molecules. I like MLC for the abbreviation of molecule. A proportion is going to show that they're equal, right? So I'm going to go moles on top, molecules on the bottom. I know 1 mole of oxygen would contain 6.022 times 10 to the 23rd molecules. So you wind up doing the same thing mathematically, right? To solve the proportion, you cross multiply, then divide. So I'm going to take 3 to the 24th, divide by Avogadro's number. This time I need how many sig figs? Just 2, right? Because of the 3.0, which should turn out to be 5.0, right? 5.0 moles of O2. Okay. I especially like proportions for a problem like this last one on here, because to me it feels like it's less work and less writing and just getting to your calculation a little sooner. So I can connect molecules and mass through the mole. So I don't have have to go to the extra step of showing molecules to moles or grams to moles, moles to molecules. I can just do it all at once, right? So I would say how many molecules of water are there in 250.0 grams if I know that there would be Avogadro's number worth of molecules in 18.02 grams of water, since that's molar mass. Right. Again, mathematically, it's going to be the same. I just like the proportions. I did dimensional analysis for years and years and years, and I love proportions now. I'm a strong advocate for them. This is like 8.55 something, right? Like that. 18.82. Oh, I entered it wrong in my calculator. Nope, 8.355. Times 10 to the 24 molecules. How do I find atoms from here? Times 3, right? There's 3 total atoms for every 1 molecule. Now, I would leave the number unrounded in my calculator and then round my final answer again for the number of atoms. This is 0.506 times 10 to the 25th atoms. Okay. Again, I don't care what you do to solve the problem as long as the way you do it can get to a right answer and that you show me what you did. All right, last but not least on this is review stuff is molarity. Molarity is the only concentration unit that we're going to use. I heard some of you talking about other concentration units like molality and mole fraction and percent by mass, percent by volume. We're not going to use those. Okay, this is the only one we need. The only one we will ever use in the lab. I am never going to make up a 3.72 molal solution. Okay? Anything that might be given to us as a percentage by volume or mass, we're probably going to use that to calculate into molarity anyways. Okay, so make sure you're using moles of solute. Make sure you're using liters of solution. Again, with this, I don't care if you show me the conversion between milliliters and liters. I assume you can do that in your head. Okay. Again, with this, we want to just highlight the fact that given the name and formula, possibly even the molar mass is going to be something you're going to see with AP problems. So here's how I would go about doing this. I would find the number of moles of rubidium chloride in 2.42 grams. If 1 mole is 120.92 grams. No, it's 0.2, isn't it? .02. 0.02001 moles. I like to take a couple extra sig divided by 0.2500 liters is going to give me 0.08